Hi everybody, in this video I would like to show you some selected examples related to bending moment in beams. Okay, in this example we have two posts, the first one and the second one. The first one is made of wood, and second one is made of aluminum. On the left side, wood post is a solid one. Inside is full. When you have cross section, then cross section is like this one. Okay, the diameter here in this case is what? D1. That's the wood post. And for the wood post, the height is given 2.5 meters and some force, external force is given 12 kilonewton is given. In the case of wood, maximum allowable bending moment is 15 megapascal. Okay, that's the wood. And on the right side we have aluminum tube. Aluminum tube is like this one. Aluminum tube is like this one. Okay, aluminum tube is like this one. When you see aluminum tube, outside diameter is what? Outside diameter is D2. D2 is given. D2 is given. And inside diameter is 1/8 D2. That means inside diameter is what? This diameter is 1/4 D2. It's multiplied by 3, and we can say 3/4 D2. Okay, that's exactly like this one. Okay, be careful about this one. And allowable bending stress is given like this one. And our final goal is to find diameter, required diameter. When allowable stress is given like that, we would like to know required diameter D1 and D2. That's our goal. And in order to find the required diameter, we can use some relationship between bending moment and section modulus. Actually, section modulus S equals given bending moment maximum is divided by what? Allowable stress. Okay, let's see step by step. On this case, wood case, we have maximum bending moment equals P, that's multiplied by H, P and H at this point. That's the maximum bending moment. We can say 12 kilonewton is multiplied H is 2.5 meters. Then this one is 30 kilonewton meter. 30 kilonewton meter. That's a value. And when you apply this formula here, S equals in the case of circle 5 D1 3/32. This one is what? Maximum bending moment, 30 kilonewton meter. 30 kilonewton meter is divided by maximum allowable stress, 15 megapascal. finally, when you convert this one 0.002 cubic meter, this one is what? Section modulus in the case of. And then finally we can calculate the D1 value. D1 value, which is expressed in millimeter. Okay, you can calculate easily D1 value there. Okay. Then first one was solved. D1. We got D1. Next case, we would like to calculate this one, aluminum case. In this case, we would like to calculate moment of inertia I2 equals what? 5 over 64 outside diameter. Outside diameter is D24 minus inside diameter 3 over 4 D24. This one is what? Moment of inertia in this case. Moment of inertia was calculated like this one. And section modulus is of course I2 over C. C equals, of course, I2 is given there. I2 over C is D2 over 2. This one is C. Then we can calculate S2 value. Of course, in the S2 is calculated, maximum bending moment is divided by what? Allowable bending moment. Maximum bending moment is same as first case, this one. 30 kilonewton meter is divided by allowable bending stress 50 megapascal. Okay, this one is like this one. Okay, when I2 is substituted there, then it is dependent upon D value, D2 is there. We calculate D2 is also here. And finally, this value is same as S2. Then finally, we can calculate D2 value, which is expressed in millimeter. That's the answer for the D2, sorry. D2. Okay. In this example, we've calculated required diameter for each case. On the left side, wood case D1 is calculated like this one. Of course, we applied S equals maximum bending moment is divided by allowable stress, bending stress. Okay. Then we found maximum bending moment like this one, and calculate section modulus, then finally calculate D1 value. Next one. In the case of aluminum, is tube is like this one. Then moment of inertia is calculated by this one, and section modulus. And similarly, we can apply external bending moment and allowable stress is substitute. Then finally, then we can calculate required diameter D2. Okay, now let's see another example. We have a dam And them is like this one. This one is side view, this one is top view. Let's consider this one is them. This one is them. This one is them. Okay, this one them was consist of some panels like this one, very long panels, which have very long panels, 1 panel, 2, 3, 4, 5, and etc. is connected. This kind of post is located 1, 2, 3 regularly, located regularly. Its distance is S. S is 0.8 meters. 0.8 meter. And total height of them is 2 meters. 2 meters. Okay. And we want to find this post size. The cross section is B by B. B by B. And of course, allowable stress, bending stress is given 8.0 megapascal. This one is given. Pascal is given. Okay, in this case, we would like to find the size of the post, the size of the cross section. How we can solve it? How we can attack it? At first, let's think about maximum bending moment. Maximum bending moment, because maximum bending moment is changed divided by allowable stress. Then we can have section modulus S. Section modulus S. This one is available. In order to apply this formula to this formula, then first let's find maximum bending moment. Okay, first let's think about this one. This one. When you consider the side view, the pressure is distributed like this one. Pressure is distributed like this one. Then you can say Q0 equals gamma H. Gamma is here, weight density. Gamma equals rho g. Rho is density and g is gravitational acceleration. Q0 is acting like this way at this point. And the force is distributed like this one evenly. Then it is equivalent like this one. This one is the area of the triangle, and triangle is what? 1/2 Q0 H, this distance. Of course, this distance is what? 1/3 H, 1/3 H, 1/3 H. Then we can calculate maximum bending moment. And this force 1/2 Q0 H. This force is multiplied by this distance S. S is considered. S. Then the distance, this distance, H/3 can be considered. Then Q0 is gamma H. This one is what? Gamma H. When you consider this one, then 6/1 and gamma 1, 2, 3 H3 and S. This value is maximum maximum bending moment, which is acting at this position, Then S value, S1, S is like this one, S is, then we can calculate S equals what? Sigma A is given like this one, 8 megapascal, or sigma A and gamma H3S, in this case, x modulus S equals what? S equals what? P3 over 6. Let's assume this one is what? Square root 1. B by B in this case. And finally, B3 equals sigma A, gamma H3S. When you substitute values for each case, then you can calculate the B value. Maybe it is expressed in millimeter. In this example, we've considered a dam. In this dam, the side view is like this one, very high. The panel is connected like this one. And we have located with some distance S the post cross-sectional is like this one. Okay, we can apply this equation first. And firstly, we've calculated bending moment. In order to maximum find bending moment, we've considered equivalent concentrated load there and applied section modulus, and finally we can calculate required dimension related to post. Okay, now in this example, we would like to calculate maximum bending stress at this point, and the maximum bending stress somewhere there inside from 0 to L, somewhere there. Let's consider at first figure itself. We have a cantilever beam, which is firmly attached at the point B. The cantilever beam is tapered beam, and the diameter at this point is dB, and at this point is dA. At the end of the cantilever beam A is located like this one. We have a beam like this one. Beam is tapered one. What's tapered? The slope is very small. If it's very steep, then it's impossible to apply here. We apply another theory related to theory of elasticity. Okay. We have this kind of condition. Diameter dB is 2dA. At first, let's calculate dB, sigma B. Stress B. In order to calculate sigma is calculated by maximum bending moment is divided by section modulus. In the case of section modulus, of circle, S equals 5 over 32 D3. Okay, at this point, P is multiplied L, that's PL, that's the moment. And section modulus in this case is what? 5 over 32 D B 3. When you dB equals 2 dA, this one is what? 2 dA. Then we can say this one is 8 and 4 PL 5 dA cubic. This one is what? At this point, bending moment, bending stress. Next term, we would like to calculate maximum bending moment somewhere inside. Now let's think about some point somewhere here, x. Here we would like to calculate the diameter first. Diameter, let's say, is dx equals, last time we've already deal with this kind of diameter, dA plus dB minus dA is multiplied x over L. In the case of torsion, we've considered about this kind of relationship. And section modulus Sx equals what? This one, 5 over 32 dA plus dB minus dA x over L. This one, in the case of this one, is 3. Of course, this one is what? dB minus dA. dB minus dA equals, this one is what? dA. When you rearrange this one, 5 over 32 dA 3. Then this one is 1 plus dA is over there, x over L 3. Okay. X over 3. Then we can calculate at this point sigma value. Sigma, let's say x. Sigma x equals what? Px is divided by what? This value. 5 over 32 dA 1 plus x over L 3. We apply this kind of relationship, Px is multiplied by Sx. And in this equation, sigma x is changed like this one. Sigma x is like this one. And we want to calculate maximum value of sigma x. In order to that, we can take derivative d sigma x dx equals 0. Then you can calculate x equals what? L over 2. You can get L over 2. L over 2. When you substitute this one there, sigma x equals px over 5 over 42 dA, and x equals L over 2, x equals L over 2, L over 2, and plus x equals L over 2 is divided by L, 3. We can delete this one. Then finally we can get sigma x value. Okay, we've seen here maximum sigma value and maximum bending stress, and at this point maximum bending stress. We also applied here this kind of relationship. We start with diameter and section modulus. Let's calculate like this one. We derived sigma x and take derivative, finally get some solution where the maximum value happens. Then if we substitute it there, then finally we can get sigma x value like this one.